Hello. Purpose of today's video lesson is to recap what we've learned about exponential growth and try to fit it into our newest topic, which would be exponential decay. So just to recap, again, exponential growth functions follow a format. It's kind of like linear functions in that there's a starting value or y-intercept, and then there's some sort of factor that shows increase or how fast the function is going to increase. So unlike linear functions, instead of adding over and over again, we're going to be multiplying over and over again. So here we have 0.944 in this particular case refers to public debt from the 1980s. This is really old data. It doesn't really matter that much. But let's assume that these data are reliable. X represents the years after 1980. So the data were entered into the graphing calculator and a regression was run, exponential regression. TI will oblige by giving you A times B to the X, just like we said. Gives us our A value, gives us our B value. What's left for us to do is to interpret the meaning of these numbers. The 0.944, for example, represents the public debt in the year 1980, which we would translate as $0.944 trillion, or in other words, $944 billion in debt in 1980. The 1.135 is the growth factor because it's factoring in, it's being multiplied over and over and over again every year after 1980. And that represents the growth factor. As I said, that means the annual growth rate was 100% less than that. So instead of 0.1385, we write that as 13.85%. Last year's debt will be retained. That's 100% of last year's debt, plus an additional 13.85% of the debt added to it. So that's how we interpret the values A and B in the context. Once we know an exponential growth curve, we can answer any kind of question. For example, we could say, project this debt into the year 2012, 32 years after 1980, and that would show $60 trillion in debt. Thankfully, the actual debt in 2012 was $15 trillion, considerably less than the $60 trillion projected, which means the rate of growth in the debt is far, far less than it was in the 1980s. Furthermore, we could also ask questions like, well, when was the debt, or when did the debt reach $5 trillion, assuming that we had the same annual growth rate, and we can use intersection. We don't have the algebraic skills right now to solve this equation, but we can, however, use intersect to find out the solution to that equation. And it turns out 12.8 years, or somewhere in 1992, there should have been a $5 trillion debt. Anyway. This page is in your notes, your handout, and it's basically a full summary of everything we need to know thus far. We talk about the general format for exponential growth functions, what the A and the B values represent, how to describe graphs of exponential functions, and how tables of exponential functions can be observed, and so on. Also have the difference between growth rate and growth factor, and then we also have little techniques for graphing exponential functions given the A and B values that we have. So I encourage you to either pause this page and read this page, or find this page in your notes and study it, because these are all the different facts that you are responsible for. If you read one of these sentences and you really don't understand it, then you need to find out what's going on and ask the appropriate authority on the matter. Moving on now. When we study exponential growth in the form A times B to the X, in order for us to have growth, we need to have the condition that B is greater than 1. This condition is important because if B is a number bigger than 1, for example, and I'm just going to write off on the side here, if B is greater than 1, like 1.2, then when you multiply a number like A equals 10 times 1.2, you get 12. 12 is bigger than 10. So when you multiply by 1.2, you end up with a larger number. Now, if B was 0.75, and we multiply 10 times 0.75, we end up with 7.5. We notice now we ended up with a number that's smaller than 10. So if we multiply by numbers smaller than 1, we end up with smaller results. If we multiply by numbers bigger than 1, we end up with bigger results. And so in order to have an exponential growth function, we need the condition that our b value must be greater than 1. Not greater than 0, but greater than 1. Oops. Anyway, that being said, what if I had a function that was written as 1 times 1/2 to the x power? This 1/2 now represents our b value, and our b value is not greater than 1, so now the issue is, what happens? What kind of function am I going to get here? It's not going to be growth. That's one thing I know for sure. But here's what I can figure out. I can actually make a table of values using what I learned about exponents. I'm going to start with f of 3 down here. F of 3 is going to be 1/2 to the 3rd power, which is 1/2 times 1/2 times 1/2, which is going to be 1/8. Now, I could actually figure out then that 1/2 to the 2nd power is going to be 1/4, 1/2 to the 1 power is going to be 1/2, 1/2 to the 0 power, well, that's easy. That's not 0, that's 1. Now I got to figure out what 1/2 to the negative 1 power is. And the negative means divide or reciprocal. So we could look at 1 divided by 1/2, and we could ask how many halves are there in 1? The answer is 2. Can probably infer then that 1/2 to the negative 2 is going to be 4, and 1/2 to the negative 3 is going to be 8. Now if I were to plot these data, when x is negative 3, y is 8. When x is negative 2, y is 4. Negative 1, 2, 0, 1, 1, 1/2, 2, 1/4, and we end up with an exponential growth curve that looks like this. Well, that's exponential, not growth. It's doing the opposite of growth. This is what we actually call exponential decay. And exponential decay is oftentimes used in things like carbon dating. When we find something old, you can use the decay of the carbon atom or something to figure out, carbon-14, to figure out how old something is, because it decays over time. Anyway, I digress. Quick observation. This is a function that has a b value that's definitely less than or greater than 1, but there is a negative in front of the exponent, which means I have to do a horizontal transformation here, horizontal flip. I'm going to end up with a graph that looks just like this, reflected over the y-axis. Now when I look at that closely, what I realize is these two are the same graph. So I get exponential decay when the b value is less than 1, or I get exponential decay if the b value is greater than 1, but the exponent coefficient is negative. So in other words, to summarize, if we have, hold on a second. If we have 2 to the negative x, that's really 2 to the negative 1 to the x, which is 1/2 to the x power. And so here we know 2 to the negative 1, or sorry, 2 to the negative x is equal to 1/2 to the positive x. So no matter how you slice it, these are both examples of exponential decay functions. So here's a quick summary of what the difference is between exponential growth versus exponential decay, and how to look at an equation and determine whether it's growth or decay. So let's take some things we learned before about growth rate and growth factor. In this function, a times b to the x, the a is 4, we start with 4, and then we double, so this would be like the 4 bacteria that double every 15 minutes. The growth factor in this case is 2, which basically says we're going to double, over and over and over again, we double. Well, that means that the growth rate is actually 100%, because each generation we keep 100% of the original 4, plus an additional 100%, and that gives us a total of 200% growth. So the growth factor is 2, the growth rate is 1, aka 100%. Similarly, we have here a population problem, 32,000 some odd, with a 4% growth rate. The growth factor being 104%, the growth rate being 4%. So here's what I figured. If I add 1 to my growth rate, I get a growth factor. In other words, if I add my growth rate to 100%, that becomes the growth factor. Well, we can use similar reasoning to talk about decay. First of all, when I look at 89.7 times 0.64 to the t, this is actually representing the height or rebound height of a ball that's being dropped. I can here determine that initially the ball was dropped from around 90 inches, 89.7 inches. And what this says is, after one bounce, we will have 64% of the original drop height. We keep 64% of our original drop height. So in this case, if I keep 64% of what I drop, that means I lose 36% of what I drop. So the decay factor is 0.64, and the reason I know it's the decay factor is it's the b value. It's the number being multiplied over and over and over again. Factors are multipliers, so we're going to keep multiplying the factor over and over and over again. The decay factor is 0.64. The decay rate is 100% less the 64% that we kept, which means we lost 36%. So here, what's the difference? We're going to keep 100% plus an additional 4%. That gives us growth rates and growth factors. Here, we're going to keep 100% less 64%, which means we lose 36%. So basically, we subtract to find our decay rate from 1. We add to 1 to find our decay factor. That's kind of confusing. There's a lot of vocab in there. You need to get your vocab straight before you can understand it. But suffice it to say again, all this information is in your notes. I encourage you to read, digest, scoop your own ice cream, if you will. Just to drive this point home, I would like to look at number 6. 6 is talking about a pendulum, and it says, each time a pendulum swings from right to left or from left to right, the ball of the pendulum will reach an ever-decreasing height. What I learned here is a pendulum similar to the one shown started at a height of 8 centimeters. It loses 18% of its height after every swing. So here, what I have to do is ask myself, if I lose 18%, and we start at 8 centimeters, we're going to take y equals 8 centimeters, and then we're going to basically take our 100%, which we will write as decimal, and then we are going to lose 18%, which we will also write as a decimal, and we'll do that for every bounce. So in other words, we're going to take our 8 centimeters and we will keep 82% or 0.82 of the original 8 centimeters by the first bounce. Second bounce will have 82% of 82% of 8 centimeters, and so on and so forth. So the equation for number 6 is going to represent here basically a decay factor of 82%, and that's 82% of height kept. And that means we have a decay rate. That means 18% of the height is lost in energy. So that should hopefully clear up the difference between decay rates and decay factors. Try to connect it to what you know about growth rates and growth factors. The more practice you do, the easier this will be. So hope that's helpful. Have a good day.